Hi there. We examined topic 14, our question being, explain why for some constant k, the language b, which is w1 to wn, then repeating the first kw inputs, where w is a binary string, is regular. To determine that for some constant k, the language b is regular, we must first understand the expression. Arbitrarily, we can pick some example numbers, k equals 2, n equals 4, w equals 1001. K is an arbitrary constant, w is the input string, n is the length of the input. We can now split the binary input strings into index steps, then process the input. w1 is 1, w2 is 0, and so forth. We take the first k characters, w1 and w2, in our case, 1, 0. We can then append these to the end of our original input string, resulting in the accepted state 1001, 10. In simple terms, words in the language repeat the first k letters as a suffix. Where the entire input string is processed, then the first k inputs are repeated at the end. The expression essentially repeats the first k inputs based on the string w after all n characters are displayed. To prove that this expression is regular, it is vital that k is constant and unchanging. A language is regular if it can be recognized by a DFA. The properties of regular languages are close under concatenation, union, and the clean star. And every NFA has an equivalent DFA from theorem 1.39. If instead k were a variable, the automaton would not be able to handle the language as regular. This is due to the automaton being unable to adapt to various values, as it can only keep track of a finite number of characters denoted as states. Since the number of states must be finite, the automaton can only store a constant amount of information. For a case where k equals to 2, input equals 1001, we can analyze the converted NFA. In a general case, to convert the expression into an NFA, we can split the process into two main aspects: the storing of k inputs, then the concatenating of the first k inputs. In the initial phase, there are 2 to the k possible k patterns for the automaton to save. This is due to there being 2 possible inputs, 0 and 1, and k possible values to save. After the initial phase of reading k inputs, the inputs then loop over themselves, completing the total input string. After looping, inputs then transition into an epsilon transition, which is necessary since the NFA needs to guess non-deterministically when the input string is ended before verifying the last k inputs. Then the last few states accept the corresponding k-bit pattern. Since this expression can be converted to an NFA, an existing DFA exists due to theorem 1.39. This guarantees an equivalent DFA exists, which proves that the expression is regular. If we follow along with the example, the highlights indicate the path that the input 1001 would take from Q1 to Q2, from Q0 to Q2, where 1 and 0 are the initial k inputs, then looping over the rest of the string. Then an epsilon transition, where the NFA guesses where the initial string ends, then Q13 takes in 1, then being accepted after taking the last 0. This line is only accepted when the prefix and suffix match.
Hello everyone, my name is Palkar and I'll be taking over the presentation. Here we'll discuss the case where k is equal to 2 for deterministic finite atonement. In this situation, the atonement only needs to remember the first 2 bits of the input string. Over here, since we are working with binary, there are only 4 possible prefixes, which is 0, 0, 0, 1, 1, 0, and 1, 1. According to that, the DFA branches into the 4 cases based on the first 2 symbols of the input string. As it moves on and reads the entire string, at the end, it compares the last 2 symbols, which is the suffix, to the stored prefix earlier. If they match, the string moves into the accept state, and if they don't, it is rejected. For example, here the example is 1001, which is the prefix is 10 and suffix is 01, which gets rejected, and the string which is 1010, the prefix and suffix are equal and matches and moves into the accept state. Over here we have the visual representation of the case where k is equal to as a state diagram. As we can see, the process begins by reading the prefix and then transitions into one of the memory states. For here, if we take an example of the prefix 10, the atonement follows the path into the memory of 10 and then it reads the entire length of the string. Once it reaches the end, it moves into the checking state, and if the suffix matches with the prefix, it moves into the accepting state for that specific prefix. This visualization is a good example to understand and visualize how it stores the prefix and reads the input and then compares the suffix to the prefix. Over here, I'll briefly go through the program that was used for developing the diagram in Python. So over here, we used GraphViz library, which is an open source library for visualization, which helps in representing structural information and graphs. Over here, we have created a function that is used for setting up our diagraph by giving the instructions, reading from left to right, and the size. Then on we have states, which has start state, each part of the prefix, and different for prefix states. Then we have the accept state list, which contains the accept state for all the four prefixes. From there on, we have the start entry point, which has the label for start, and then there on gives the name label for each state. And then from there on, it moves into reading the transition state when it initially starts the graph, and moving from there, it identifies the prefix and enters the main loop. And similarly, it has a transition for each specific case, from 00 to 11, and then finally it renders the DFA graph in a PNG format as an output. Here we'll discuss the case where k is equal to 3 for DFA, and before that I can tell you that the logic is exactly same as the previous case, but over here the machine needs to remember 3 bits instead of 2, which means it has 8 possible prefixes ranging from 000 all the way up to 111. It has their own branches. Once it moves to the entire length of the string, it reads the prefix and the suffix and matches. From there on, it moves into accepting state. But the only difference we notice over here is with one increment of k, there is an increase almost double the possible prefixes, which shows an exponential growth in the size with one increment of k. Here I'll be talking about the conversion of NFA to DFA, why it is important and why we should do so. Building a large DFA could be a bit difficult, so we start by solving the problem in terms of NFA. And NFA has the ability to branch non-deterministically, which means it can start checking the suffix at the right position without remembering everything, and then this makes it easier to design an NFA that stores prefix and guesses the end of the input. And by theorem 1.9, which is from our textbook, which tells us that every NFA has an equivalent DFA. So if we have an NFA that recognizes this language, we know that there would a DFA exists, and that ensures us that the language is regular, even though the result for DFA could be large as well. So here are the learnings from this assignment. We have learned that DFA only needs to store a fixed number of symbols. In this case, it's the prefix of length k. Secondly, we know that the number of state grows exponentially with k, but still it remains finite, which is the key property that makes the language regular. And finally, by theorem 1.39, we know that NFA and DFAs are equivalent, and that helps us knowing the regularity. Hence, we have formally proved that the language is regular for B. This is the workflow from our team. We started off with a discussion of how we would solve a problem and then laying out different strategies. From there on, we did our research online as well as using lecture notes and textbook to get a better understanding of the topic. We got some feedback from the class, which also helped us refining our approach. Halfway, I decided to implement a Python script which helped me develop the graph. This was done with the help of Google's Gemini Assistant as well as using Google Colab for getting the output, and thereon we worked together to help get a better and final report for the assignment as well as this presentation. Here are the tools that we used for this assignment: Microsoft Office, Python, Discord for team collaboration, Google's Gemini, and Google Colab for code development and assistant. Here are our references, and thank you for listening to us. Hope you have liked our explanation for the topic, and hope you have got it useful information from this assignment. Thank you.